All right, we will get started. So more people may be joining. Let me share my screen. All right. So good morning, good afternoon, or good evening, everyone. Thanks for joining this webinar. Many of you are regular attendees. So this webinar series is on geoenvironmental engineering, polluted land, waste management, sustainability, and resiliency. So I'm sure many of you are getting benefited by these webinars in terms of getting new ideas for research, and also learning about research methodologies. We have recorded the past webinars. You can go to this YouTube channel and view any webinars on any topic that you may be interested. I think we have close to 70 webinars that are recorded and made available on this YouTube channel. So I request you to use this resource, to enrich your knowledge, and perhaps think about doing research in different fields. So if you are interested in doing research in geoenvironmental engineering, and if you want to know what are the topics, and these webinars will be a great resource. So coming to today's webinar, as of this morning, we have 537 registrants from 50 countries for this webinar. Actually, today in the morning, I looked at registration list and I counted the countries. If you wonder which are the 50 countries, these are the countries. It's really heartening to see people joining from different parts of the world, and including all continents, Africa, and other remote countries. So some of them cannot join live because of the time difference, but I'm happy to see the presence of conference attendees from different countries. So please you mute your mic and switch off your video during the webinar. And at the end of the presentation, we will have a question and answer session. You may not be able to type questions during the presentation, but you can unmute and ask your questions once the presentation is done. And then we will open up the chat box so you can type your question, and make sure your question is directed to everyone so that everyone can see your question, including the presenter. So presenter will answer at the end of the presentation. Thanks again for joining this webinar. So regarding today's topic and the presenter, today's topic is effective control of landfill gas dispersion and volatile organic compound transport using innovative geomembranes. So it's kind of a very nice topic, a very timely topic in many developing countries where landfill gas control is extremely important. So our presenter today is Professor Jongwan. Is a professor in the Department of Civil and Environmental Engineering at the University of Nebraska, Lincoln, Omaha, here in USA. So just a brief bio of Professor Jongwan. Dr. Jongwan is an associate professor in the Department of Civil and Environmental Engineering at the University of Nebraska, Lincoln. He received his PhD in Civil and Environmental Engineering with the emphasis on geoenvironmental engineering from the University of Wisconsin-Madison. He received MS from the University of Texas at Austin. He has over 15 years of professional and academic experience in geotechnical and geoenvironmental engineering. He worked for Dongwon E&C company for more than 3 years as a field engineer at infrastructure construction projects in South Korea before coming to the US. And then after his PhD, before joining UNL, he was a research faculty at New York University, Abu Dhabi campus. He taught fundamental engineering subjects, and he led a global research project on oil recovery enhancement and innovative farming systems with renewable energy. So that was a kind of a nice experience for him to have before taking up the faculty position in the US. Um, and Dr. Yun's research interests are waste containment systems, contaminant transport, and radioactive disposal facilities. His research results have been published in over 50 national and international journal papers and proceedings. So Dr. Un is a member of two technical committees, the Geoenvironmental Engineering Committee and Unsaturated Soil Mechanics Committee of Geo Institute ASCE. So I got to know him very well through his participation in Geoenvironmental Engineering Committee. So Dr. Un is an associate editor for the KSCE, Journal of Civil Engineering. He's also a reviewer for several journals, including Journal of Geotechnical and Geoenvironmental Engineering, Journal of Contaminant Hydrology, and Construction and Building Materials. In addition, he is a board member of the Nebraska ASCE Geo Institute Committee, and he is also a member of the Solid Waste Association of North America. And with this very brief introduction, I request Dr. Un to share his screen and present it. I will stop sharing my screen. Again, before he starts, on behalf of all the attendees, I want to thank him very much for taking the time to give this presentation. Thanks, everyone.
All right. Thank you, Dr. Reddy, for the kind introduction. So let me share the screen. I changed the full. All right. Can you see the full screen?
Yeah, it's good.
All right. Okay, so good morning, good afternoon, good evening from all over the world. So the colleagues from the Geoenvironmental Engineering. So I'm very pleased to have a chance to present my research today in the international webinar series on the Geoenvironmental Engineering. So my topic to present today is effective controls of landfill gas dispersion and VOC transport using the innovative geomembrane. So I am a Jongwan, associate professor in the civil and environmental engineering at the University of Nebraska Lincoln. So this topic I worked on the more than 10 years since I was in Wisconsin and still in Nebraska. So I'm very pleased to present this topic. So I believe that many of attendees here so well know about the landfill, MSW landfill. So MSW landfill is an engineering containment system to dispose of household waste, also the non-hazardous waste, like common waste, and also it's a regulatory base compliance with the federal regulations. In the United States, we have an AQUA and the state government to act, so we enforcefully regulate at the facility. So usually the landfill consists of the liner, cover, and other facility like gas collection system and leachate circulation system. So absolutely needs to manage the leachate and the landfill gas. So this is the cross sections where I get the diagram from EPA. So the landfill is one of the most complex facility in the civil engineering. So you can see that it consists of the covers and liner, multiple barrier system with, as I mentioned, the gas collection system and leachate circulation system. So in operating landfill, so you can see that we have a multiple barrier capping. So in the cover, so we have a geosynthetic geomembrane, and then the liner, so we have a HDP geomembrane with a compacted clay liner. So in the operating landfill, we usually use interim and intermediate cover, soil or the soil polyethylene sheet. So here's you can see that the cross sections of the barrier system at the line and cover. So this is the photo to construct the composite liner system in the landfill. So you can see there's a compact clay liner and the geomembrane and the GCL. So what's the concerns for the liner of the landfill. So there's a concern about the leakage of the volatile organic compound. So this is the actual field observations. So you can see the bar graph shows the concentration distributions of the 21 most frequently detected VOCs in rigid collected from the MSW landfill in Wisconsin. So you can see the thick horizontal line, each box represents MCL, maximum contaminant level, for the compound, and the Wisconsin ES enforcement standard was used for the VOC, not have the MCL. So median concentrations, as you can see, the median concentrations of the 6 VOCs are above the MCL, and the median concentrations of the 4 VOC exceed in the Wisconsin ES. So according to the previous research, so the diffusive transport of VOC is dominant mode in the composite barrier compared to advective flow through the defective hole. So you can see this graph. So here is the concentrations, mass flux. So in the through the defective hole, but you can see the diffusive transport of the VOC is way higher, several order of magnitude higher than the defective hole, advective flow. So, so what about the cover? So, you know, the nowadays is getting more attention of the climate change due to the greenhouse gas. So surprisingly, you can see the chart in 2020. So the landfill emit much GHG, followed by the oil industry and agriculture in the United States. So almost 70 to 20% of the methane emissions comes from the landfill in the United States. So you know, the 45, approximately 50% of landfill gas is methane. So you know, the methane is 20 to 30 times more potent than carbon dioxide as a GHG. So not only for the greenhouse gas, but landfill usually have suffer for the odor problems. So this is a survey conducted by EPA. So to the resident near the MSW landfill. So what is the most abundant common problem in the landfill is the odor. So bad odor. So more than like 26% respond that pointed out that problem. So what is the trend? What is the situations in the world, country around the world regarding the GHG emissions? So in the United States, in Biden administrations rejoined the Paris Agreement and then try to decrease the GHG emissions in half by the 2030. And also the other countries, major countries like China, so they also regulate CO2 emissions, and also EU and overall the world reduce the effort to reduce methane emissions to limit global temperature rise. So what about the detail in the United States? So EPA cracked down on the landfill methane emissions, so, and also several state department government try to enforcefully regulate, reduce the gas emissions, especially California and Florida. They have take actions to reduce the gas emissions. So what about in my state, Nebraska? So recently, in Omaha, we closed the Sarpy County landfill because of the odor issues. Many complaints comes up. Finally it's closed. So, and also we regulate the gas emissions by the state act. So this is also issues over the states. So how we can control the landfill gas? So we can use gas collection system. So we install the pipe So vertically and horizontally, we sucked out the gas, and then we use this methane to generate electricity, which is good. But there is a much uncertainty of the system. Also, still there's a fugitive gases not neglected. So as an alternative, so new materials as a cover and bottom liner is being introduced. The new material is ethylene vinyl alcohol, the copolymer geomembrane, EVOH geomembrane. So EVOH is a copolymer materials has a having polarity because of the hydroxy group. So using the co-extrusion technique, so you can see that the geomembrane configuration is sandwich type. So the outer layer is a common polyethylene, and inside the very thin film of the EVOH. So EVOH is not the new materials. The other industry widely use the materials to mitigate and minimize the gas emission. For example, like food packing and the limited oxygen transport, and also the vehicle, the gas tank. So inside of the tank coated by the EVOH, and then minimize the VOC transport, the gas transport. Okay, so these materials induce the two benefits: property of the polyethylene as water, the polar barriers, and while having the potential to substantially reduce the transport of the non-polar chemical contaminant. So when we apply the EVOH geomembrane on the landfill barriers, so EVOH expected to reduce the VOC migration through the bottom layer liners, and then the gas emission, landfill gas emission to the atmosphere through the cover. So the EVOH, as I mentioned, is being introduced, and then it's very limited cases to apply this one. But there are a few, but one example to implement these materials in the Lumpkey sanitary landfill in Ohio. So, you know, the Ohio landfill, Lumpkey landfill is notorious to have a lot of the issues like the MSW fails and the fires and others, and then the operator, Lumpkey landfill, decided to install the EVOH cover in the landfill, and then they have some successful results. So here is the older complaint at the Lumpkey landfill. So they installed the EVOH cover 2013 to 2014, and then there was a significant improvement in the odor situations near the residents. So the area covered, the odor complaint hotlines is covered like 22 acres. So, but still there's a lack of the fundamental study for the EVOH geomembrane in terms of the transport phenomenon and then field applications. So with that, today research, we're focusing on the 4 tasks and objectives. So the first objectives, we evaluate and compare transport rate for the common VOC in composite liners with EVOH and HDP geomembrane. So with that, task 1 that I present, liner experiment of the composite liners with the EVOH and HDP geomembrane. And second objective, to compare the landfill gas emissions to the entering cover with a different type of the geomembrane. So with that, task 2 is the cover experiment of soil with the EVOH and PE geomembranes were conducted. And third one, the evaluate compare landfill gas emission through the entering cover with the EVOH and LLDP geomembrane in field. So we prepared the field pilot test of the entering covers with the EVOH and LLDP geomembrane, and then evaluate the gas emissions for 3 years. And finally, so we evaluate and compare the landfill gas dispersion through the entering cover with the EVOH and LLDP geomembrane in regional scale. So we conducted gas dispersion modeling to how much the landfill gas dispersed in regional area. Okay, so for test one, line experiment for the aqueous VOC transport. So for this test, we conducted the bench scale column test to simulate the bottom liner. So we put the compacted clay liner underlaying the geomembrane and GCL, and then the top is we have aqueous VOC in upper reservoir, and periodically we collect the sample through the sampling port. So this is the diffusive experiment. We allow the diffusion from the top reservoir in the aqueous VOC through the multiple barriers. So during the test, we rotate the steer bars, and then maintain the same concentration. And also we have a effluent bag to maintain the saturated conditions, even we extract the sample during the test. So this is a very innovative design and newly constructed. And also the sampling port is newly designed, customized. So you can see we have a sampling syringe here, and we have a two-step tub, and the brass connector and the cap was induced in the two-step tub. So, and then to install the geomembrane, so we split like two compartments, and then we put the Teflon gasket on the top and the bottom, and then we minimize the mass loss during the test. We carefully control that the loss during the test of the VOC. So here's the testing programs for the line experiment. So we conducted the two different geomembranes, EVOH and HDPE, and 1.5 millimeter. And also we put the compacted clay liner and the GCL, and with the attenuation layer. So absolutely we duplicate the test to assure that repeatability, reliability of the test. So we tested 5 different VOC, which are representative type of the VOC detected in the lice meter in Wisconsin. So the MC, MTBE, TC, toluene, and chlorobenzene. So those are all representative different type of the VOC. And also this is the microphoto of the EVOH geomembrane. You can see that inside there's a white film, the EVOH materials, and then surrounded by the PE materials. And this is the setup VOC diffusion contest in the environmentally controlled the room in the lab. So we prepared the 21 columns for the test. And then, so this is the graph shows the reliability, repeatability of the diffusion contest. So we collect the concentrations of the VOC, and then with time, so we have a breakthrough curve through the compacted clay liners, and then the white symbol and the black symbol shows the repeated test result. And then we back calculate, inversely estimate the diffusion coefficients of this one, and then compare to other researches, and then diffusion coefficient of the 1.5 millimeter, the HDP geomembrane is quite good agreement with our testing result. Okay, so this is the breakthrough curve concentration versus time for the test. So here's shows the effect of the EVOH geomembranes with the compacted clay liners. So you can see this is the breakthrough curve concentration increase over time through the HDP geomembrane. So we have a breakthrough curve around 50 days, and so depending on the different type of the VOC, we have a different breakthrough time, but mostly occurs like less than 50 days. However, in the EVOH. So we have a much later, breakthrough curves around the 150. So, and then also the increasing rate of the concentration is much lower in the EVOH than the HDPE. So this graph shows the effect of the hydrophobicity on the breakthrough time. So depending on the type of the VOC, we have a different polarity, and then we have a different breakthrough time. So with that, for left graph shows the breakthrough time versus the solubility, which stands for the polarity of each VOC. And if we have a higher polarity, we have a lower breakthrough time because the polarity maybe affect the EVOH and then change that the breakthrough time. So, and then a compacted clay liner has a lower breakthrough time, and then the geosynthetic clay liner is a more like longer breakthrough time. So these are the opposite. I mean, the EVOH and HDP shows us some opposite trends of the hydrophobicity. Okay, so this is the comparisons of the EVOH diffusion coefficients between the EVOH and HDP geomembrane. So based on the result of the count test, we inversely estimate the diffusion coefficient. So you can see the diffusion coefficients of EVOH are 20 times smaller than those for the HDPE. So far, we conducted the bench scale count test, which is like much thinner than the actual practice. So we conducted the numerical modeling, the selected VOC token. So to simulate the transport, VOC transport in the actual case scenario. So we conducted the 1D diffusion modeling by the FDMs, and then we described this cell using the Crank-Nichols method, and then we put the initial and boundary condition like this, and then for the transport parameters, we obtained from the literature and our research. And then we simulate the different compacted clay thickness according to the LACRA and Wisconsin DNO. So these are the results of the comparisons total and transport with the composite liners between the 0.6 meter and the 1.2 meter thick compacted clay liner. So as expected, the thicker layers has a more like thinner layers has a more like increased concentration. So you can see the LACRA regulations MSW for HDP geomembrane, so we can have a breakthrough curve like this, and then rapidly increase that concentrations over time, so 100 years. And then EVOH is a lower increase concentrations. If you have a thick the compacted clay liners, according to the Wisconsin DNO, so you have a less concentration increase, but still the benefit of the EVOH is clear. So EVOH geomembrane helps to reduce the total and contaminant migrations at 100 years to level between the 40 to around the 40% lower than the migrations given by the HDP geomembrane. So what about the equivalent diffusion coefficients of the this co-extruded EVOH geomembrane? So using the mass conservations and fixed laws, so we derive that the equivalent diffusion coefficients. So harmonic average rules. So we propose estimate the equivalent diffusion coefficient of the co-extruded geomembranes using this equation. So it's validated and confirmed by the testing results. So here's the the equivalent diffusion coefficients of validation. So here is the calculate the diffusion coefficient here using the previous equation, and this is the measured diffusion coefficients from the lab test, and then you can see that there's a good agreement between the calculate and measured diffusion coefficient, and also by using the diffusion coefficients of VOC to predict the concentration increase over time is also a good match with the laboratory test. So conclusions of the task 1. So VOC breakthrough occurs substantially later with the EVOH geomembranes, approximately 150 days versus the HDP geomembranes, 35 days. So transport of the VOC from composite liner is much lower with the EVOH geomembrane. The rate of the transport consistent with the hydrophobicity of the VOC, and diffusion coefficient of the EVOH is 20 times smaller than the HDP geomembrane. And according to the numerical modeling, the EVOH geomembrane reduced the total and contaminant migrations approximately 40%. Okay, so equivalent to diffusion coefficient estimated by the proposed equation is good agreement with the measured one. So for the second task, we conduct the column experiment for evaluating the gas emission. So similar to the liner experiment, we prepare the column like this, but here's the source of the contaminant is the bottom. So we allow the methane and the hydrogen sulfide bottom, and then allow the entering cover, so soil and the geomembrane. So we measure that the concentrations in the top. So here's the testing programs of the column test for gas. So similar to the liner test, we prepare the EVOH geomembrane. It's a thinner because of this cover material. So and LLDPE and PVC and EVOH. And without the geomembrane, so we conducted as well as a control. So these are the testing setup of the column test. And also you use environmental control room in the lab. Okay, so this is the concentrations increase of the H2S and the CH4 methane through the composite cover. So you can see this is log scale right graph, and then concentration increase, relative concentration increase through the soil here. And then if we have the polyethylene, the common geomembrane, so we have a breakthrough curve like around 7 days later, but still like EVOH is breakthrough, but it's still like not increase a lot. So still maintaining the very low concentrations. So concentration increase for the methane through the entering cover. You can see the concentration increase is much several orders of magnitude lower in the EVOH compared to the common geomembrane. And breakthrough time and rate of concentration increase for the hydrogen sulfide through the entering cover. You can see the breakthrough time is way longer compared to the common geomembrane for the EVOH. So, and also the concentration increase rate is much lower in the EVOH compared to the other geomembrane. So also we conducted methane flux modeling through the cover. So methane flux through the cover, so we simulate the 1 foot set soil with the geomembranes. And then you can see the geomembrane is, so EVOH is around the 2 order magnitude smaller flux compared to the common geomembrane. So conclusions of the task 2, breakthrough and the rate of the transport in the soil much higher than with the geomembrane present. And EVOH delays the breakthrough time effectively compared to the other geomembrane. So order of the diffusion coefficient, HDS and CH4 is P is higher, LLDP, PVC, and EVOH geomembrane. The EVOH geomembrane has around 2 order magnitude smaller diffusion coefficient compared to the other geomembrane, and also the vacuum flux for the numerical simulations are around 2 order magnitude smaller in the EVOH geomembrane. So with those laboratory testing results, we move on the field pilot test in Butler County Landfill in Nebraska. The study was carried out at the operating landfill, Butler County Landfill, so which is around 1 hour driving from the campus, and it's a rural areas near the David City, and the measured methane contents of the is around this 56%, and the area of the pilot test is around 10K square meter. So this is, excuse me, got water. So this is the cross sections of the field testing instrumentations. So we prepare the trench like this, and then over the waste body, we deploy the geomembrane, and then overlaying the geomembrane, we cover the dirt soil. And then we put the flux chamber for the static gas monitoring. So here's, and then the size of the, we minimize the size boundary effect, and then the pilot testing, the site is like 30 meter by the 100 meter. And also we have some trench to minimize the boundary effect like this. So this is the plain view of the flux chamber, static flux chamber installation. So we have a different set of the cover. So the width is 30 meter, and then the length is around 100 meter, and then this black dot and white dot shows that locations of the flux chamber. So we have 3 testing sites, a different type of the geomembrane and no geomembrane, and also we have 5 different cover type. Means we have some chambers without the soil and some chamber with soil. Okay, and this is the installation procedure. So the geomembrane cover system, and then the static chamber. So we really careful to install the flux chamber to the geomembrane. So we have a unique the sealing techniques with the bentonite and the silicones here. So we very carefully to install that as flux chamber. So okay, so this is the video. I'm not sure how many you guys to see that the geomembrane cover system installation. So this is the way to install the geomembrane in field. So I just start the video to see. So first we're rolling out the geomembrane on the waste body, and then fortunately there's a slope, so the rolling is ultimately going on the bottom of the slope. Okay, so this is one of the test site to install the geomembrane. And also we use a chemical analyzer to measure the concentrations of gas. We use a gas chromatography and Jerome H2S analyzer. And okay, so this is the methane concentrations in the embedded chamber. So we measure the source concentration underneath the geomembranes in the waste body. So it's like half 1.3 meter below that the cover geomembrane, and then you can see we monitor the 3 years terms discontinued monitoring. Unfortunately, at the time, so the COVID pandemic hit, and then we university and other like state agencies regulate the field monitoring activity, so we cannot measure, and also continuously, and also we had some flood issues a couple of years ago, so we have a very struggle to keep monitoring that one, but we still continue the data monitoring so far. So, and the field monitoring data shows that around the 50% by the 50% of the methane and carbon dioxide. And also we can collect the gas in the gas collection system. So we have some concentrations of that. And the H2S concentration in the embedment chamber. So unlike the methane and carbon dioxide, so the H2S is shows some dramatic change. So initially the concentration of methane is really the H2S is really low, like around the 5 ppm, but there's some new collections wells near the embedment chamber, so we have some reductions of the source concentrations of the H2S. And also we realize if we have a soil cover in the chamber, so we have some significantly large amount of the carbon dioxide. So we guess this is because of the methane oxidations from the soil bacteria, and then the methane converted to carbon dioxide. We consider this kind of change in the adjust, calibrate this change to the measurement data. So this is the average methane concentrations in the flux chamber. So for the different type of the cover. So we conducted monitoring for the 3 years discontinuity, but considering methane oxidation, so you can see the first year here. So for like around 7 months, you can see the soil alone here. So we have a very high increase of the methane concentrations compared to LLDP and EVOH. So if you convert that amount of the concentrations of percent, like soil alone is 100%, and LLDP is 0.16%, and the EVOH is 0.06%. And year one like this, and then this is if we have a soil in the chamber, LLDP has a little bit much larger concentration compared to just LLDP, and it is the same as the second and third year. And based on the field monitoring data, so we have this breakthrough curve of the methane concentrations over time. So at the first 7 months data acquisition, so we estimate the diffusion coefficients of soil and the different geomembrane. You can see that the comparisons of the measured data and existing data is not well matched, but because of this maybe the field the uncertainties. So let's move the task for the landfill gas dispersion modeling near the bottle count landfill. So objective of this task, we are going to simulate, evaluate the odor dispersions from the operating landfill, considering the environmental factors like topographic and weather and temperatures and source concentrations changed by the different seasonal cycle. So hypothesis is applications of the intermediate cover constructed with the EVOH geomembrane reduce the spread of the odor near the landfill effectively, but performance of EVOH varies depending on the season. So with that, we have the framework of the gas dispersion modeling. So we input different environment vectors like methodological data and topographical data and gas emissions obtained from the actual field site. And then we do the safety modeling with the Lagrangian Navier-Stokes equations. And also we apply the fixed second law to disperse gas, and then modeling the dispersed gas, and also we apply the three different cover type, soil and LLDP and EVOH. And this is the site locations that we simulate. And as I mentioned, we have a bottle counter landfill in the David city. It's just a rural area. So we simulate the 50 kilometer by 50 kilometer from the source. And then in the upper area, so there's a natural preservations in the rivers, and then there's a small elevation change. So importing the digital elevation model, DEM, into the console to construct the 3D numerical model about the landfill regions. So you can see that this is the DEM data, and the white spot shows that the bottle count landfill. And influence the wind and the topographic on the methane dispersion is simulated based on the CFD module in the console. So we put the meteorological data like wind directions and magnitude for the different seasons. So we are the weather station in the landfills, and then we collect the data, and then we realize that most of the wind is focusing on the north directions and south directions. So summer and fall is more frequently wind, south wind. So source concentrations of the hydrogen sulfide for the odor gas, we obtain that value from the actual measurement and also consider the previous research. So we have the around 6.5% of soil alone for the EVOH is less than 1% of soil alone. So this is the result of the gas dispersions, so contour. So you can see the just the soil alone without the geomembrane. So impact area is largest. Okay, so the 50 kilometer by 50 kilometer, you can see that so this is the ppb. So here is a most dark red line shows that 100 ppb the contour line, and the 50 ppb contour line and 10 ppb contour line. So we are focusing on the 5-mile circle comparison later on. So these are the result, the summer and winter for with geomembrane. So different type of geomembrane you can see compared to soil alone. So these are the red line shows the soil alone, and then blue lines the EVOH, and the yellow lines the LLDPE. So you can see the in summer, so we have a more strong wind than winter, so we have a more like widespread of the gas, odor gas in the area, but still like very limited dispersion area using the EVOH compared to the soil alone or LLDPE. So we counted for the dispersion area of the different covers with a threshold like 10 ppb. So in spring, summer, fall, and winter, the odor area of the cover using LLDP geomembrane is around 1 to 2% compared to the soil alone. Okay, but if you have a EVOH, we have at least 10 odor lower than the LLDP is 0.2, 0.3 of soil. Okay, so the odor area of the cover using EVOH geomembrane is around 14 to 16% of the using the LLDPE. So also we survey the complaint from the residents. Okay, so this is the complaint maps near the landfill. So this shows that locations of the landfill, bottle count landfill, and then we counted the complaint number. So the landfill was constructed early 2000, and then get the waste till like 2010, and then nowadays getting more like complaint number. So surprisingly, the complaint, the residence is very related with the wind data. So it's located like north and south directions. So good argument with gas dispersion model. So we counted the number of the residents in order area of the different cover in the different seasons. So we use the GIS data obtain that informations of the residents, and also we apply application of geomembrane can reduce the number of the residents affected by odors, especially the geomembrane. You can see without the geomembrane, so we have a affected area. In the affected area, the influenced resident number is at 920, but in that area, so the odor area is decreased, and then residents number is significantly decreased. EVOH is only like 6 households affected. So what about the cost effectiveness of EVOH geomembrane? So we use LF cost web model, and then we put the some initial costs and maintain and everything's there. And then you can see applications of the geomembrane can increase accumulated cash flow by the selling methane gas produced from the gas collection well. So initially, without the geomembrane covers, the initial cost is much higher than the soil only, but after a payback period, and then you can see increase the accumulated cash flow is much higher when we have an entering cover with the geomembrane. But EVOH is most highest among those treatments. So also you can see the MPV change with the greenhouse reduction credit, and then using the EVOH was more profitable and beneficial to the overall revenue of the landfill based on the result of the comparing the MPV and cash flow. So conclusions of the task 3 and 4. So average concentrations of methane in soil alone at least more than 2 order magnitude higher than the LLDPE and the EVOH. And also the compare with the soil alone covers, EVOH and LLDPE has a much significant enhancement, reduce the methane emission. And field performance, EVOH geomembrane is continuously investigated right now, and the EVOH geomembrane cover delays the breakthrough time effectively compared to other geomembrane. And also the applications of the geomembrane highly reduce the odor gas dispersions, especially EVOH can reduce odor area by almost 90.8%. And the use of the EVOH geomembrane can significantly reduce the number of the residents affected the refugee odor. And EVOH geomembrane can potentially used as an intermediate cover for operating landfill to reduce the odor issues. And using the EVOH was more profitable and beneficial to the overall revenue of the landfill based on the result of the comparing MPV and cash flow. So with that, the EVOH applications on the landfill barrier is very effective and significantly reducing the non-polar organic contaminant compared to the conventional geomembrane. So I acknowledge the sponsors of the project, especially most of the funding comes from the Nebraska Environmental Trust in the state foundations. And also I would like to thank for Wisconsin Medicine, and also financial support the University of Nebraska Foundation, and also material support from the vendor like Query and Raven Industries, and also some partial support from the REU from the NSF. So those are the publications so far we have regarding this topic. And thank you so much for your attentions. I think it's all my presentation. So this is a photo that I took in the installations of the covers in the bottle count landfill. So thank you.
Very nice, Jongwan. Very, very nice work. So a lot of very carefully designed lab experiments, and most importantly, doing something out in the field. That's a real world case. And then you also did dispersion modeling. So it's very, very nice, very comprehensive. So I am asking people to type their questions in the chat box. You can